So, in the last lecture we were discussing mixing in a reactor, okay, by an impeller. How do we calculate the power that is required for mixing of the fluid in the reactor based upon the properties of the fluid, the length dimension of the reactor, the size, and the rotation rate. Okay. And based upon that we had got a dimensionless group, the power number, which is equal to power divided by rho times Fr cube times T power 5. Okay. Note that power has dimensions of mass, length square, T power minus 3. If we scale the power number by inertial scales, this is what you will get. This is the power number. Consistent with all the momentum transfer quantities we have been scaling with inertial scales, the friction factor, the drag coefficient, the skin friction coefficient, etc. In a similar manner, this power required for rotating the impeller is also scaled by inertial scales in the power number. That is in general a function of the Reynolds number. Okay. In this particular case, the Reynolds number is defined as rho f d square by mu. Okay. So, the rotational frequency times the diameter is a velocity. So, rho into velocity into d by mu is the Reynolds number. And when you scale up a reactor, so if you want to construct a large scale reactor with a particular dimension and offhand you do not know what the power required for that reactor will be. So, you start off by scaling by constructing a scale model for the reactor, determine what is the power required for that scale model, and then have the ability to relate the power for the actual reactor P A with the power required for the model reactor. Okay. So, that is how you would do the scale up. And in this particular case, you do not keep dimensional quantities the same between the scaled and the actual reactor. Okay. Dimensional quantities will in general be different for similarity, dimensional similarity. What has to be kept constant is the dimensionless groups, the relevant dimensionless groups. Those have to be kept constant between the small reactor and the large reactor. If you make the relevant dimensionless groups a constant, then the power number of the actual reactor will be the same as the power number of the model reactor. The power will not be the same. Okay. You cannot relate dimensional quantities. It is the power number that will be the same between the model reactor and the actual reactor. So, we did an example where we calculated what was the power required for the actual reactor, how it was related to the power required for the model reactor. That is a reactor with an impeller. We want to design one with diameter 1 meter to rotate at a frequency of 1 second inverse. Okay. A diameter of 1 meter to rotate at a frequency of 1 second inverse, mixing a liquid of density 10 power 3 kg per meter cubed and viscosity 1 kg per meter per second, and liquid air surface tension was 0.1 kg per second square. So, in order to find out what is the power that we require to predict the power required for the large scale reactor, we designed a smaller reactor of diameter 10 centimeters, 1/10 that of the large scale reactor. And then we conduct experiments on this model reactor, determine what is the power required for this model reactor, and based upon that predict what would be the power required for the large scale reactor. And in this case we had estimated the quantities. One is of course the power number, the Reynolds number, which is a ratio of inertia and viscosity. We saw that that was 10 power 3 for this particular case. When the impeller rotates, there is a deformation of the interface between the liquid and the ambient. That deformation depends upon the centrifugal forces and the gravitational forces. It is determined by a balance between centrifugal forces and gravitational forces. That ratio is the Froude number, okay, Fr square d by g, the square root of. Okay. The velocity is square divided by gd, and we substitute velocity is Fr times d. Okay. And then there is the Weber number, which is the ratio of inertial and surface tension forces. We had put in the actual numbers for these. The Reynolds number was 10 power 3, Froude number was about 0.3, and the Weber number was 10 power 4. Weber number is very large, implies that surface tension is most likely not important in this case. Froude number is comparable to 1. So, gravitational and centrifugal forces are comparable, and therefore, the Froude number has to be maintained between the model reactor and the actual reactor in order to get the correct shape of the interface. Reynolds number is 10 power 3. You would think viscous effects can be neglected, but that is not always the case. As we saw, for if you have a slender plate moving in a fluid, the shear stress is primarily viscous because the projected area is small, and in that case viscosity is important. If you had something like a sphere or something, or moving, or a plate moving perpendicular to the flow, then of course there is a Reynolds number range where viscous forces are not important. So, it is necessary to keep the Reynolds number as well the same between the actual and the model reactor. So, we had used the subscript m for the model reactor, a for the actual reactor, and based upon the Froude number being the same, we had estimated what is the ratio of frequencies. Turned out to be square root of 10, okay, because that is equal to the ratio of the model and the actual reactor frequencies is equal to the square of that is equal to the ratio of diameters for the Froude number to be the same. And so, we found out that the operating condition for the model reactor has to be at a frequency of 3.16 second inverse. To make the Reynolds number the same between the model and the actual reactor, we had got a relationship between the kinematic viscosities of those two. Kinematic viscosity is ratio of viscosity and density. Okay. And as I said, in most cases liquids have approximately the same density, so it is necessary to keep the ratio of viscosities as 0.0316 for the model reactor. Okay. The viscosity to be used in the model reactor is much smaller than the viscosity to be used in the actual reactor, because in order for the Reynolds number to be the same. And if we keep the Reynolds number and the Froude number the same, the power number has to be the same. Okay. And on that basis we had estimated what is the power required. The power number for the actual reactor is actually more than 3000 times the power required for the model reactor. So, if you make a measurement on the model reactor and get a certain power, the actual reactor you have to design for a power that is more than 3000 times that. So, that I showed you how to do scale up of a reactor. Okay. These impellers in reactors, okay, are also used for breakup of droplets in emulsions, etc. Okay. Apart from mixing different fluids together, they are also used for homogenizing the system, okay, reducing the size of the bubble or the droplet, etc. Okay. So, typically what you would do is put two liquids in here, okay, two usually immiscible liquids like aqueous solution and a fat solution or something like that, along with surfactants, and then you rotate the impeller. Okay. And if you look what is happening close to the impeller, okay, you are generating a flow field. Okay. You are generating basically some kind of a shear flow field, okay, in the vicinity of this impeller. Okay. And so, any droplet that is caught in this flow field will get expanded and then broken up, okay, into two droplets. Okay. So, that is the mechanism locally by which droplets are breaking up because of the turbulent shear that is created within the impeller. Okay. And this droplet breakup does not depend, or the average droplet diameter that you get, okay, the average droplet diameter that you get does not in general depend upon the total size of the reactor, but rather it depends only upon what is happening in the local environment, okay, of the droplet. Okay. It does not depend upon the large scale flow, it depends only upon the local environment of the droplet. Okay. What is holding the droplet together is surface tension. Okay. Surface tension tends to reduce surface area, return the droplets to its spherical shape. Okay. What is tending to break up the droplet is the shear that is generated, okay. Either the inertial or the viscous stresses that are generated at the droplet scale, okay, at the small scale. Okay. So, the droplet diameter will in general depend upon a balance between the breakup mechanism and the stabilizing mechanism of the droplet. Stabilization due to surface tension and breakup due to inertial or viscous stresses, okay, depending upon which is dominant. Okay. Therefore, the parameters that are important, okay, for determining the droplet diameter, the dependent parameter is the droplet diameter d, okay. Independent are the fluid properties rho, mu, surface tension. Okay. These are the fluid properties, and there is also one other parameter that is important, and that is what is called the energy dissipation rate. Per unit mass. Per unit mass. Okay. Energy dissipation rate has dimensions, the same dimensions as power. Okay. Energy dissipation rate has same dimensions as power. M L square T power minus 3. Okay. Therefore, the energy dissipation rate per unit mass has dimensions of L square T power minus 3. Okay. So, there is the droplet diameter here. Okay. The density has dimensions m L power minus 3, m L inverse T inverse. This is m T power minus 2, as you recall. Okay. And the energy dissipation rate L square T power minus 3, the energy dissipated per unit mass. Okay. So, this is an intensive variable, okay. It is equal to the power input. Power input is basically the energy dissipation rate, because whatever power is put in at steady state is dissipated, okay, by the fluid velocity. Okay. So, this is basically the power divided by the total mass, okay, of the reactor. So, this diameter has dimensions of L, and I have 1 dependent and 4 independent, okay, 3 dimensions. I should have 1 dependent and 3 independent, 1 dependent and 1 independent dimensionless group, okay, from this, because there are 3 dimensions, 1 dependent property, the droplet diameter, and 4 independent parameters. So, now this depends upon what is the mechanism of breakup. Okay. Is it inertial or is it viscous? Okay. So, that will determine what dimensionless group we get. Okay. If the Reynolds number based upon the droplet diameter and velocity is large, okay, if the Reynolds number based upon droplet diameter and velocity is large, you would expect the breakup to be primarily due to inertial effects. Okay. If the diameter based upon, if the Reynolds number is large, okay, if it's large, okay, breakup due to inertial. Okay, breakup will be due to inertial effects. Okay. That means that the dimensionless parameter, okay, the dimensionless parameter the dependent dimensionless parameter will be a function of the droplet diameter to the first power, the dependent group can be written to the first power, times epsilon power A, okay, times rho power B and the surface tension power C, okay, is equal to a constant, if we can neglect viscous effects at the droplet scale. Okay. And we have to determine A, B and C from dimensional analysis. Okay. So, length dimension is L, this is L square t power minus 3 power A, m L power minus 3 power B into m t power minus 2 power C is equal to m power 0. Okay. So, therefore, for the mass dimension I have B plus C equal to 0. For the length dimension I have 1 plus 2A minus 3B is equal to 0, and the time dimension I have minus 3A minus 2C equal to 0. So, this gives me basically B is equal to minus C, this gives me 3A minus 2C by 3, and then I have to substitute that into this equation. I will get 1 plus 2A plus 3C is equal to 0. Okay. And ultimately, if you solve all of these equations, you will get A is equal to 2 by 5, okay. B is equal to 3 by 5, C is equal to minus 3 by 5. Okay. So, that is the final solution of these equations. So, that means that rho power 3 by 5, okay, epsilon power 2 by 5, droplet diameter divided by gamma power 3 by 5 is equal to a constant. Okay. And if you know what this constant is, you can then estimate what is the droplet diameter. Okay. There have been studies which have measured this, and they show that the constant is approximately equal to 1.1. Okay. Therefore, the droplet diameter is equal to 1.1 gamma power 3 by 5 by rho power 3 by 5 epsilon power 2 by 5. Okay. So, that gives you an empirical correlation for estimating based upon the energy per unit mass, okay, what is the droplet diameter. Okay. And this estimate of course assumes that this epsilon is somehow a constant value. That is not strictly true. Okay. In the reactor, the energy dissipation rate will in general depend upon position. Okay. You will get higher energy dissipated in regions where there is higher flow and higher straining, and lower energy dissipated in regions where there is lower flow. Okay. This epsilon that I have here is the energy dissipation rate total power divided by the total mass. Okay. And therefore, this energy dissipation rate has to averages over the spatial variations, it is an average quantity. The droplet diameter is also an average quantity. There will of course be some variation in the droplet diameter depending upon whether the droplet was formed close to the impeller or further away and so on. This correlation gives you the relation between the average droplet diameter and the average energy dissipation rate. Okay. And using this you can do scale up. Okay. So, once again for a given configuration, the relation between the local energy dissipation rate and the power that is input will be different depending upon different configurations. Okay. For a fixed configuration, you can do a scale up to determine the relation between the droplet diameter and the power required. Okay. Okay. So, let us look at an example. Okay. A mixer of dimension of diameter dA, that is the actual diameter, and frequency FRA, okay, is to be designed for breakup of droplets with maximum size D max. Okay. A scale model with dm is equal to dA by 10, okay, provides droplet breakup maximum size D max when operated with frequency FRM. Okay. What is the frequency of the actual mixer FA? Okay. So, basically this question is that I have a actual reactor diameter dA, and I need to decide what frequency I have to operate the actual reactor at to get a droplet size D max. So, I made a scale reactor 1/10 the size. I know that if I operate it with a frequency FRM, okay, then I will get the correct droplet size D max for the smaller reactor. What should the larger reactor be operated at, okay, to get the same size? Okay. So, how do we solve this problem? First thing, the droplet diameter depends on the surface tension, the density, and the energy dissipation rate per unit mass epsilon. Okay. So, those are the dependent parameters. As long as these three are kept a constant, you will get the same droplet diameter. Okay. So, between the actual reactor and the model reactor, I need to keep the surface tension, the density, and the energy dissipation rate per unit mass the same, provided the breakup is happening in the inertial regime where inertial forces are important or are dominant. Okay. That will not apply in the viscous regime. Okay. This will apply only in the inertial regime where the inertial forces are dominant. So, if I keep these parameters a constant, okay, then the droplet diameter should be the same. Between the scale reactor and the actual reactor, let us say that we use the same fluid with the same surface tension, the same mixture with the same surface tension, then rho and gamma are the same between the two reactors. Okay. What that means is that the energy dissipation rate per unit mass in the model reactor has to be the energy dissipation rate per unit mass in the actual reactor. Okay. What is the energy dissipation rate? Okay. That is equal to the power, okay, by rho d cubed. Okay. The energy dissipation per unit mass is the total power, okay, input divided by the unit mass, okay, and mass goes as the density times the diameter cube. This is the diameter of the impeller, okay, not the diameter of the droplet. Okay. So, this power by rho d cubed just from dimensional analysis has to scale as d square times Fr cubed. Okay. Note that this epsilon I told you has dimensions of L square t power minus 3. Okay. So, this has to scale as the diameter square times the frequency cubed. Okay. That is the energy dissipation per unit mass. Okay. That means that if I have to keep the energy dissipation rate per unit mass a constant between the actual reactor and the model reactor, that means that dm square Frm cubed is equal to dA square Fra cubed. Okay. Which means that the frequency by Frm is equal to dm by dA whole power 2 by 3. The frequency of the actual reactor by the frequency of the model reactor has to be dm by dA whole power 2 by 3, which in this case is equal to 1 by 10, because the model reactor has 1/10 the diameter of the actual reactor, power 2 by 3 is equal to 0.215. That means the actual reactor has to have a frequency which is 0.215 times the model reactor. Okay. And what is the power? The power has to be determined by keeping epsilon the same. Okay. Power has to be determined by keeping epsilon the same. Okay. That means that power of the actual reactor by rho times the diameter of the actual reactor cubed is equal to power of the model reactor by rho times diameter of the model reactor cubed. Okay. Which means that the power of the actual reactor, if we use the same density, is equal to power of the model reactor, diameter of the actual reactor by dm the whole cube is equal to 1000 times the power of the model reactor. Okay. So, if I have done an experiment in a model reactor and got the desired droplet size, with a particular frequency Frm, then for the actual reactor, that frequency can be 0.215 times Frm, because the size is larger by a factor of 10, and therefore dm by dA is 0.1. The actual power that will be required is going to be 1000 times. Okay. So, you have to design the actual reactor to actually have power input that is 1000 times what you have it for the model reactor of 1/10 the size. Okay. So, this is how you do scale up in order to get constant intensive properties. Okay. In this particular case, the droplet diameter at the microscale has to be the same. And what that implies is that at that scale the energy dissipation rate per unit mass has to be the same, because what is happening at the local scale depends only upon what the intensive quantities at that scale. And so, you have to keep the energy dissipation rate per unit mass the same between the actual and the model system. Okay. And if you do that, you can find out the relations between the frequencies for driving for the actual and model system, and you can also find out what is the ratio of the power required. Okay. So, this completes our discussion of momentum transfer in different contexts. Okay. We had looked at momentum transfer problems for flow through conduits, a pipe, laminar and turbulent flows, flow past a flat plate, flow around particles, flow through dense collection of particles in a packed column, and finally mixing for an impeller. Okay. So, this completes our discussion of momentum transfer. In the next lecture, I will start our discussion on mass and heat transfer. In momentum transfer, I had got you correlations, discussed correlations for the dimensionless momentum flux, friction factor, drag coefficient, skin friction coefficient. In heat and mass transfer, we will be discussing the correlations for the average heat and the average mass fluxes. In those cases, the average fluxes are the Nusselt number and the Sherwood number, and they depend upon the Reynolds number and the Peclet number, which are the ratios of convection and diffusion. We will continue that in the next lecture. I will see you then.